Hi everybody, I'm Muhammad, and in this video I'm again going to talk about CFD solution for the heat transfer diffusion equation. But this video is a bit different from my previous videos because I'm not going to talk about MATLAB much. Actually, what I'm trying to say is about the occasions that we cannot apply the central differencing method in our discretization. If you are not familiar with discretization, a short explanation is that it is the process of turning a continuous differential equation into a discrete one. I mean, we do some mathematical operations, so we can turn the differential equation into a system of linear equations, so we can solve it easily. But if you need more explanations, I highly encourage you to pause this video and take a look at my previous one where I talk in detail about the discretization method. So if you find this video helpful, please do not forget to share and subscribe, and if you have any question, leave a comment. I will try to answer it as soon as possible. Okay, the first equation you see here is the heat transfer equation, diffusion equation, and I talk about it in detail and deeply in my previous video. The first term is the change with respect to the time, and it's gonna be 0 because we are interested in a steady state equation. The second term is convection, and the first term after the equal sign is the conduction term. The involvement of convection term is also taken into account in this video, but I'm not going to solve it step by step. I just shortly show you we need to just take integral from both sides and use the divergence theorem that again I talked about it in my previous video. And if we do the same steps like the exact same steps like my previous video, you can come up with this table, and the results are summarized here where the coefficients of left and right and other coefficients are shown. I use these coefficients in order to write a MATLAB code, and in this MATLAB code again to just shortly explain what we're gonna do. Actually, we define a matrix for coefficients, a matrix for unknowns, and a matrix for the solutions, and then by the use of these coefficients, which are shown here, we define each element of the matrix, and then we solve the system of linear equations. As you see, for the left boundary, I define the AL, AR, and the rest, and then I define the elements of coefficient matrix and the solution matrix. I did the same for the right boundary and the interior cells, as you can see here. And then I solved this using the backslash for this is an easy part of the MATLAB code. By the way, after that I defined let's remember to remind you, this code is the exact same code that I explained in my previous video. The only changes are regarding the coefficients. I mean this f, which is added here because of the convection term. Okay, by the way, if we solve this equation, we will see that sorry, it may take a little time. Yeah, we will see that the temperature distribution is smooth using 5 mesh, but the problem for central differencing is when for example the convection term is more powerful. For example, when the speed is something around 0.3. In this case, we will see that the answer is not as smooth as it used to be. I mean, there are gonna be some unstable parts, for example, and this unstable part gets bigger at higher speeds. For example, when the speed is 1 meter per second, we're gonna face a highly unstable solution, and this is because of and in order to address this, a number called Peclet number is defined. When the Peclet number, it's defined as here. I mean, the Peclet number is the convective term over the conduction term, and it just assesses the power of convective term with respect to the conduction term. And when this number is bigger than 2, the central differencing method cannot be applied. So we need to address this by two ways. First, we can increase the number of meshes. For example, if we increase it to something around 20 or 50, for example, we will see that the Peclet number goes down to half. In this case, again, the solution is smooth. And it can be even more smooth, I think, by increasing the number of meshes even more. Yeah, it is the smoothest solution, by the way. And you can see that by increasing the number of meshes, we actually increase the denominator and decrease the Peclet number amount. But since these solutions sometimes have unstable answers, another scheme, which is called the Opwin scheme, is defined, and I'm going to talk about it in my next video. But remember that although the central differencing is more accurate, the Opwin method is the one which is more useful because it addresses these instabilities, and we are more likely to come up with stable solutions by using the Opwin method.